Let me just take a brief introduction for today's meeting. So hi everyone, welcome to our 24th SIGCOMM Reading Group. My name is Xiangyu and I am an assistant professor at Xiamen University. Today, Professor Xiang has something else to do, some emergency things. So I will host this meeting on his behalf. So in past sessions, we have talked about some really great work, such as multimodal LLM training optimization and enhancing RDMA reliability for lossy network. So today we are diving into an important and interesting topic. Actually, it is also my topic, programmable network hardware, with a special perspective on network program synthesis for heterogeneous network hardware. So we'll be looking at a great paper titled ParserHawk, Hardware-Aware Parser Generator using program synthesis, which was published in SIGCOMM 2025. So this paper discusses the key challenges of the existing parser compilers, such as improper hardware resource optimization, and present a novel approach to build the parser compiler based on the insights of program synthesis. I think both academia and the industry can learn a lot from this work. So usually our meeting is also live streamed on other platforms like Tencent Meeting and Bilibili. So we will begin with around 30 to 40-minute presentation of the paper, followed by another 30-minute discussion with the authors. So we are delighted to welcome Wang from Xiamen University, who will be presenting this paper. And most importantly, we are very honored to have the first author, Xiangyu from the University of Washington, here to share his insights and experiences about this work. So I hope you all enjoyed today's session and take away something useful. So without further ado, let's give the floor to Yao for the presentation. So go ahead, Yao.
Okay, let me share my screen. Can you see my screen?
Yeah.
Okay, let's start. Okay, hi everyone. I'm Yao from Xiamen University, and today we're gonna share this work, ParserHawk, a hardware-aware parser generator that use program synthesis to compile high-level parser specs into low-level teaching-style implementations. The key idea is to treat parser code generation as a combinatory search problem, so we can find the implementation that fit our hardware constraints while using fewer resources. So let's start with the background. And the modern networks increasingly rely on programmable data planes, such as the P4-based switches and SMILEys. These devices allow operators to define customer packet processing logic directly in hardware, and enabling high throughput and low latency data line rate. Most research and tooling focus on optimizing the packet processing pipeline, tables, actions, and schedule. However, every packet must first go through the parser. The parser fundamentally determines what information is available downstream. Despite being on the critical path, the parser generation has received relatively little attention. So, the parser programs today are significantly more complex than they used to be. Real-world people programs such as Switch.people or Say.people that will contain dozens of headers and deeply nested encapsulations and protocol-specific logic. In addition, emerging workloads like financial exchange protocols or tunneling heavy data central traffic place even more stress on parsers. As parsers complexity grows, Generating correct, efficient, and portable parser implementations become increasingly difficult. Formally, a parser processes input a bit string and produce a map from field name to extracted value. Operationally, hardware parsers are typically modeled as finite state machines. Each state extracts some fields, then performs a match over a transition key, and moves to the next stage based on the TCAN style comparisons. And this low-level execution model is what the compiler must ultimately target. Let's look at a simple example to make this concrete. For a particular 8-bit input bit string, 40 and 41, the parser works in a way. And the first parser state assign the first 4-bit to the field 0 and update the map accordingly. Since the first bit of field 0 is 0, so move to the green state and assign field 0 to the next 4-bit or 11 or 1. And finally, the parser output the parsing result that set field 0 to 0 and field 1 to 15 in decimal. For another 8-bit input string, the first parser state assign the first 4-bit to the field 0. Since the first bit of the field 0 is 1, so it goes to reject state and drop the packet. A major challenge comes from hardware heterogeneity. Different devices expose different parser architectures. Some platforms use a single TCAN table and let's allow looping within state, and others using a pipeline TCAN design where each stage is fixed and looping is restricted. And this architectural difference directly affect how deep a parser can be and how transition keys are formed, and how resources are consumed. Parser implementation that is efficient on one device may be impossible on another. This leads us to the core problem addressed by ParserHawk. How can we automatically generate correct and resource-efficient parser implementations across heterogeneous hardware architectures? Existing tools often fail in one of two ways. They generate efficient parsers that waste TCAN entries or stages, or they fail compilation and entirely under tight hardware constraints. We want a solution that is both general and robust. Let's see a better result from existing code generated by doing some basic math. Suppose the input parser does stage transition based on a 4-bit key, and each row is a stage transition row and need your 1 TCAN entry resource. The goal is to implement the parser using a few laws as possible. To generate the parser code, we first of all need to merge entries using the key mask pair. There's two ways to merge the blue part, where the first one is use 2 entry, while the second one is only 1 entry. The second way is of course preferable. And afterwards, we need to ensure that the size of the transition key per parser state should follow the hardware's constraints. In this case, we need to split the 4-bit into 2-bit. Again, there is a multiple way to do such splitting. We can check the first 2-bit of the key before the last 2-bit or vice versa. We can see that checking the last two bits first is a better choice. And to make things even more complex, multi-conditions such as extraction length and look-ahead window size need considering and make a parser generation quite a complex task. Most existing parser generators rely on heuristics. They apply local rewrite rules or pattern matching, often tied to specific application. The problem is that these heuristics are sensitive to code style and brittle and architectural changes, and unable to globally optimize resource usage. Small changes in the source program can lead to large difference in generated code. So the ParserHawk take a fundamentally different approach. Instead of asking how should I generate the parser, the ParserHawk asks does there exist a parser implementation that satisfies these constraints? We frame the parser generation as a program synthesis problem. The specification defines the correctness, and the hardware constraints define the facility. And the synthesis searches for implementation that satisfies both. And this shifts complexity from heuristic to principled constraint solving framework. The workflow has three main components. First, the front-end translates the parser specification into a schematic model, and then we combine it with the hardware profile that encodes architectural constraints. And the synthesis engine searches for valid parser implementation. Once the solution formed, the backend emits the device-specific parser code. Retargeting to a new device largely means changing the hardware profile or rewriting the components. Specifically, the synthesizer takes two inputs. Parser stack defines the input parser behavior, while the hardware implementation represents the target hardware's capability. It is a partial program asking what fields to extract and what is the transition key and what is the transition logic in each parser state. We encode in the synthesizer the counterexample guide deductive synthesis loop or CGIS loop in G3 to output a generated parser implementation. And first order logic encoding for implementation mainly consists two parts: parser functionality and hardware capability. The parser functionality encodes the parsing behavior. For example, the pseudocode shows that what extraction and what state transition in which parser state. And the hardware capability captures both common behavior across devices and device-specific constraints. Common resource-based constraints include encoding the package field extraction behavior, assign the next XB to a particular field, and move the extraction point ahead by XB. Unique constraints contain the state transition key size limit of the target device. And it uses CGIS as a subroutine in program synthesis. The CGIS device program synthesis into two phases: the synthesis phases and the verification phases, and iterate between them. Briefly, it initializes a set containing selected test case from the whole input space. Then the synthesizer phases explore a solution that satisfies for all selected test case. If it cannot find such a solution for the subset of input space, it cannot find a solution for the whole input space for sure. Otherwise, the synthesis phases would pass a candidate solution for verification to check whether there is any example that make verification fail. If there is no such example, the candidate can be regarded as the final solution. Otherwise, it outputs a counter example and the added list counter example to the set of input test case and continue this synthesis and verification loop. In ParserHawk, the input test case set consists of some selected bit strings. If the synthesis phases cannot find a satisfiable solution, that means the compilation failure, and otherwise it passes the parser implementation candidate specifying the extraction behavior and transition logic to the verification phases. And if the verification pass, the candidate's parser implementation becomes the final output. Therefore, otherwise it output a counter example B string like IK plus 1 and added into the test case set and continue the CJS loop. However, the natively encoding code generation as a synthesis problem may take an extremely long time to complete. So there is an optimization. The first one is guided transition key conjunction. In a native encoding, any bit in the packet could be selected as a part of the transition key. But in reality, the parser specification already tell us which bit matter. So if a transition condition only check the ETH type, then the bit from IPv4 source address or the payload is irrelevant to the control flow. So the ParserHawk restricts the candidate transition key to only the bits that appear in spec level conditions. For example, if the spec check the ETH type equal to 0 then only those 16 bits are eligible for the key. And this single restriction removes a huge number of meaningless degrees of freedom and immediately shrink the search space. Even after putting key bits, fields with themselves can still dominate solver complexity. Many package fields are large, like IPv4 address are 32 bits and IPv6 address are 128 bits. But often they are never used in control decision. So the question becomes if the field does not influence the control flow, why reason about its full width. The ParserHawk answer this by temporarily minimize the field width during synthesis. Concretely, if a field never appear in any transition condition, it is modeled as a 1-bit symbolic value instead of its full width. For example, the IPv4 source address become a 1-bit placeholder during synthesis. And after synthesis finish, we restore the real field within the generated parser code. This preserves correctness while dramatically reducing the symbolic complexity. And next, it addresses structural symmetry in parser implementation. In many hardware architectures, multiple parser states are functionality equivalent. This means the synthesizer may waste time exploring solutions that are identical except for where a field is extracted. To avoid this redundancy, the ParserHawk pre-allocated fields extraction to specific states before synthesis. This removes the entire classes of symmetric solution from the search space. Importantly, this optimization appears only when the target architecture supports such symmetry. For example, the single ticket table design. The effect is that synthesis focus on the hard part, the transition logic, not arbitrary extraction placement. A major bottleneck in synthesis is reasoning about constants, especially value multiplier. Without restriction, a 16-bit field introduces to the power of 16 possible constants. This is far too many. And the ParserHawk uses simple but powerful design. The parser specifications are already enumerate almost all meaningful constants. So instead of synthesizing arbitrary values, the ParserHawk restricts constant to the value that explicitly appeared in specification. And the valid hardware compliant subrange derived from learn when with limits apply. For example, if a ETH type is compared against 0800 or 86DD, the resolver never considers other values. This collapses the numeric domains into a small and thematically meaningful set. So far, we've talked about which bit and which value method. So next is focus on how bits are allocated to states. Natively allocating bits individually is disastrous. Each bit can go to multiple states, leading to expectation and combinations. ParserHawk instead allocates groups of agent bits from a state field as individual units. For example, the entire 6-bit ETH type field is treated as one group. This measures how real parsers operate and reduce computational exposure from per-bit to per-field decisions. The optimization is especially important for multiple stage and family parser architecture. The final two optimizations address the remaining sources of complexity. First, vulnerable learn fields are difficult for solver to reason about. The ParserHawk simplifies learn by treating where bits as fixed with bits during synthesis. After synthesis, variable length schematics are restored in code generation. And the second one is even after outputting constant synthesis can still be expensive. So ParserHawk parallelizes the search. It fixes subsets of master variable and runs synthesis in parallel and stops as soon as one valid solution found. This turns the solver time into a knowledgeable resources and make things practical in real environments. Here are some experiment results. There is a 58 benchmarks based on fragments of existing open source puzzle programs by writing them in semantic preserving way. And the puzzle it compares the ParserHawk against both academic and commercial compilers over this benchmark. So it mainly checks two dimensions, whether or not the compiler can generate code for multiple target devices and how many resources are used for generation and code cost time. And the ParserHawk can generate the code for the parser architectures, terminal and IPO. The terminal is the single TK and IPO is the pipeline TK. Let's show that the ParserHawk can retarget multiple devices and only need to change less than 100 lines of code to reflect the architectural difference between the terminal and IPO in the ParserHawk. And in terms of the resource usage, the ParserHawk successfully compiles all benchmarks, but the commercial compilers fail to compile 20% of all benchmarks. But it takes around 8 seconds for baseline compilers to compile complete code generation, which is faster than ParserHawk. Fortunately, with all optimization enabled, 19% of all benchmarks completed in less than 5 minutes. And this work is also qualifies the benefits brought by all developed optimization. The results show that the all optimization gives over 300 CVR on average and do not introduce actual resource usage for all benchmark. And besides that, there is an experiment breakdown analyze to see the speed of each efforts for selective optimizations. Right now, we can see we choose this transition synthesis discussed before and bit group by default and enable optimization expect these two and then enable bit grouping and the state transition synthesis separately to find that each learn can offer over 10 times CVR. To conclude, this paper built a ParserHawk, high quality and targetable and parser generator for terminal and IPO using program synthesis and incorporate several domain-specific algorithms to speed up the process and achieve order of magnitude improvements in compilation time. That's all. Thank you.
Okay, great. Yeah, thanks for the great presentation, Yao. And now we are very happy to have the first author, Xiangyu, here to discuss this work. So does anybody online have questions? You can just unmute and say it, or type it in the chat box. Yeah. No questions? Yeah, so let me just ask a warm-up question. Yeah, Xiangyu, when I first look at this paper, the first thing that come into my mind is that is it possible to use natural language models to conduct the code synthesis? that we can somehow generate the intermediate representation or the code that are already optimized based on the hardware resource constraint. Yeah, I know this is a little bit ambitious, but whether do you think it is possible, or could you please share your opinions on that?
Yeah, that's a very good question. I think LLM-driven code generation is very promising. At least I tried half a year ago, and right now I tried again. I found the capability of LLM increase a lot. So in this scenario, first of all, the paper was written 1 year ago, so at that moment, LLM is not that powerful. And second, I think in this compilation process, correctness is very important. Plus like optimization. So the reason we pay for the program synthesizer, like longer code generation time, is because it can guarantee the semantic correctness plus somehow optimize the resource usage. But LM is relatively bad, still bad at that, meaning that this can sometimes generate close to correct result or close to optimal result, but it's still I would call it the last mile gap is still there. So what I think can be useful here is first we can use LM to driven the code generation, to driven the program synthesis procedure. So this can guide the program synthesis to find the correct result. And second, I think if we like y'all mentioned the CJS loop. So we generate something, we verify something, and then we generate again based on the verification results. So if we can feed the LM into that procedure where we ask LM to generate something, and then we write a verifier to verify, hey, whether the generating result is right or not, then we can ask LM to generate another way. So maybe feed the LM into as a subroutine will also be useful. That's my
I totally agree that but actually I think there might be two things that we need to consider. The first one is what kinds of model we can use. I know that now actually some of my students have tried to use LLMs to generate code based on paper itself. So they have tried of course GPT-3 and Gemini, and actually now they found that Claude is better actually. So I think in the future there might be better model, right? So what is the fundamental things here? Yeah, we know that the models will be better and better. Yeah. And what do you think is the fundamental things?
So I think here is the case. So the fundamental thing I'm thinking is first, right now I use P4. This is a domain-specific language. I think what you try most to regenerate code coming from some mainstream languages like C, Python, or other system languages. Those languages have more benchmark to train, but I think for these niche domains, they are still in lack of examples for the LM to get the correct result. So that's one thing. Maybe we should add more benchmarks for these models to know. And second, I think the hardware architecture is also very new to the language. Like yes, what I mean is you not only need to write a semantic correct or like syntactically correct for the P4, but also you need to make sure that, hey, your register style is I call hardware aware, meaning that makes the compiler happy. So that's the second thing. And the third thing is right now we still rely on the P4 compiler, so we might need to know what optimizations they are doing. So in order to make it happy, we need to generate something which is compiler aware as well. So
that's the problem. But actually, how do you decide the LM generated code is accurate in terms of
Oh.
P4 compiler. Yeah.
Oh yeah, so accurate. So basically, yeah, right now is we can write what I write is write a simulator to I mean in this case in CS2 is I encode the generated P4 program and then my specific input P4 program, and I just simulate hey for all the packet whether there are some inconsistencies between the original program's output and the generated program's output. If there is some inconsistencies, meaning inconsistency, I mean for the same input they have different output, I will just add these examples to in this case to the test set to say hey you should also make this test case work. But I think Era maybe have more fancier ways. Maybe they can check the syntax tree. You can check, check which part are hit.
Okay. Yeah. Just out of curiosity, do you think it is possible to use some, for example, verification framework to verify the output of the code synthesis?
Yes, I already use. So in this case, I use Z3, which is STM, which is based on SMT solver.
SMT solver, yeah.
Yeah, to check because so in this case I think so. The reason we guarantee the correctness is we use SMT solver to check the generated code is correct. So I think they use some brute force or like some other ways to brute force ways to check all the input and output relationships and make sure that they are correct. Yeah, I just want to add a little bit more to this part. So my previous work is focused on using so basically program synthesis it appears in most of my papers, and previously I used program synthesis to generate code for packet processing pipelines of the programmable device. So in this case, I use program synthesis to generate code for the parser part of the programmable device. So this hopefully complete the story, but I'm also exploring some optimization opportunities between the parser and the packet processing pipeline, because I'm thinking that some of the parser's functionality might be able to apply it in the packet processing pipeline and vice versa. So this can we can do some like joint optimizations across parser and packet processing pipeline. So hopefully synthesis can also play a role in that domain. But that's I think the story, the background behind the Yao's presentation in this case.
Yeah, wonderful. That makes me think a lot. Yeah. So in terms of the insight of program synthesis, how do you find this problem and come up with this idea to tackle this? Yeah.
Oh yes. So so the definition of the program synthesis is people write a high-level language, a program in high-level language, and you generate a semantically equivalent candidate, but that follows your constraints.
Yeah.
So what I am thinking is here. So first of all, this domain is niche, meaning that like parser only support extract some simple behaviors, collect some data from the input packet bitstream and then assign it into the variables. So this means we don't have too much flexibility for the program synthesis to choose. So this can simplify their program synthesis task, and this makes the program synthesis faster. And second is the reason in this domain is they have relatively high requirement for the optimizations, meaning that we really want to reduce the resource usage. Like in parser might be the number of TCAM entries, number of parser stages. And so we want program synthesis to try to find a relatively optimized result in compared with some rule-based translations. And third one is we can see that most of the programs in the programmable network domain, they change less frequently. So,
yeah.
so even though we spend a little bit more time for the program synthesis to find a relatively good result, that's like acceptable because we only need to maybe synthesize it once and then use it for relatively long period of time. So, so that's why I think maybe parser program synthesis is a good fit in this domain.
Yeah. Okay, I got it. So another following question. Do you think in which scenario is the program synthesis will be useful?
So I think when so program synthesis, so for example, I still take this scenario as an example. So if our target is heterogeneous but similar, program synthesis is very useful. So consider you write a translator, like you write a GCC backend from scratch. You write a P4 program from scratch. People have a lot of backend. So when you target from BMV program to V1 model to eBPF to different type of backend, you have to technically change your code generation procedure because their backend have different instruction set, different memory architectures. But in this case, we only need to twist the program synthesis a little bit to reflect the hardware's capabilities. So if we have a lot of backend, that's pretty good because you don't need to reinvent the view. You can leverage a lot of stuff from beginning. But I remember in some scenarios, like people only have one backend, and then program synthesis might not be that useful because they can specify a lot of heuristic, specify a lot of rule-based, only to optimize that backend. Then program synthesis maybe hey, it's too slow, something like that.
Yeah, so when there are many, for example, switches that comes from different generation or from different vendors, you think the program synthesis will be useful, right?
Yes.
Yeah.
Like
So
here, I choose switch from, I mean, not switch, IPU from Intel and switch from Tofino. I mean, sure, Intel and Tofino, they are the same thing, but they come from different sources and then their architecture are significantly different. There's might be also like Pensando, SmartNIC. Maybe.
Yeah. So did you consider SmartNIC?
Yes. I mean, IPU is already a SmartNIC. Is already a NIC.
Yeah. I know IPU. Other SmartNICs such as Bluefield 3 or Pensando.
Yeah. I'm seriously thinking about that as well.
Yeah, this actually remind me another work from NSDI 2025, and the system name should be Alkali.
Oh,
from
Alkali.
Jiaqi, Alkali.
Yeah.
It proposes a new intermediate representation that can be optimized on heterogeneous SmartNICs, right? So here from high level, will it be possible to use program synthesis to tackle the same problem and give a better optimization? Yeah,
I think so. I think that's highly possible. I mean, Alkali is also one of my related work. I think I'm mentioning in my paper. So so that's something I am thinking about. So I think they are mostly, Alkali is mostly for the other part of the hardware architecture. They do mostly for the packet processing pipeline, but we are doing the parser compilation. So I think ParserHawk is complementary to this Alkali as well.
Yeah, I know. Alkali focuses on the actually SmartNIC specific architecture.
Yes.
Yeah. So they consider heterogeneous onboard resources such as accelerators and memory hierarchies. Yeah. So actually, I'm also considering if we have a cluster of heterogeneous SmartNICs. So we need to build a centralized controller to offload our network programs onto this cluster of heterogeneous harmonics. So it is very hard from high level to just offload, for example, the C-based or Docker-based code to a FPGA harmonic. Right? That is actually very difficult. So here, if we can use some techniques like code synthesis, do you think what will be the key challenge? Yeah.
So
For example, we have a cluster of Bluefield 3, AMD Pensando, and Phoenix FPGA harmonic. Yeah.
Yeah, so yeah, that's something really interesting. I have a rough thinking about it. So there's one paper, I think it's called Clara in SOSP 2021. So
Yeah,
they
from
use some
Yimin Cho. Yeah.
so they use some machine learning based techniques to decide which part to offload to Smartnik. So so I mean I'm seriously thinking about using program synthesis to decide which program to offload to Smartnik. And I think so that's very high level idea brainstorming. So a lot of papers mention some distributed training in LM domain. So sure, we are not doing some training for the LM domain, but they definitely have some strategies to say that, hey, we have a heterogeneous, like in their domains, we have a heterogeneous GPU, how to allocate the training task to different type of GPUs. And here is we have one centralized network functions, how to maybe distribute them to different type of SmartNICs or something. Maybe we can leverage some of the insight from that domain as well. But I haven't taken a closer look at that case.
From high level, there should be I think there should be the intermediate representation. Between the high level lateral function and low level hardware architecture. So I think the key challenge might be how can we design such intermediate representation. So actually I encountered this problem before. I actually considered to manage a cluster of heterogeneous harmonics on the onboard resources. There be onboard CPUs, ARM cores, hardware accelerators, and actually P4 pipelines. So finally, I choose to use DPDK like representation to build the program, but forget about the hardware accelerator. The hardware accelerator is only fixed function. In my scenario, fixed function. So I didn't build my network the whole network function to the accelerator, to the FPGA. So I think that there should be a problem if we can if we can use some tactics to offload the C-like lateral functions to the FPGA, for example, FPGA or P4 pipeline, that would be very useful.
Right. That sounds interesting.
I think there might be two directions. The first direction is about programming language, the compiler. Another one is should be the overall cluster-wise resource management. So
makes sense.
Yes. Okay. And so let me just ask another questions about eBPF. Actually, this also remind me the eBPF. We know that eBPF is a very, very useful tool that offload to the point that near the network, right? So for example, XDP, right? So I noticed that there are some work that tries to use eBPF as an intermediate representation to the FPGA harmonic. Although I have reviewed that paper, but that paper is not published actually right now. So some people are trying to do that. So here here if we consider using eBPF to as the representation, and here's the thing, we can use code synthesis to generate eBPF code. Then if we can build a bridge between the eBPF to the and the, for example, FPGA semantic. So now the task will be how can we generate
EPF.
code eBPF code,
Yes.
based on the high level, for example, template, NF template, or NF description. So
Yes.
here, if we consider this scenario, what in your opinion will be the most challenging thing?
So I think the thing is for eBPF, it's mostly the C-like language.
Yeah.
So they have much more flexibility. So in hardware, we can say, hey, the hardware is the parser is only doing some simple job. Even in the packet processing pipeline, they are doing some simple job. But eBPF, their function is super complex. So eBPF can support a lot of, and plus they have a lot of helper functions, inline functions. So I am not sure whether we can encode the whole capability of eBPF as a program synthesis search problem, because that will blow up the search space. But if we have a lot of insight about, hey, for example, this program might only hit some subset of the eBPF functions, like for example, eBPF is an extension of classical BPF program, and the classical BPF program have much more restricted functionalities, and a lot of domain-specific languages will turn to the classical BPF programs, and in that case, I'm pretty thinking about the program synthesis techniques to generate optimized classical BPF programs. And in our domains, we can also see like, hey, if our target is a restricted part of the eBPF programs, so maybe program synthesis can also play a role in that case.
That makes sense. Okay, so now that there is a question from the audience actually. The question is, theoretically, is this system not limited to parsers, but applicable to entire complete P4 programs? If applicable, how long might it take to compile a program similar to netcache? If not applicable, what are the main limitations?
So I think it's applicable because my previous work, I think Chipmunk in 2020, SIGCOMM, they target at the code generation for pipeline. And previously, so right now we are targeting the parser. So if we target both parser and the packet processing pipeline, I think it's close to it, but we tried similar size programs. So in the packet processing pipeline should be around 5 minutes. In the parser should be around also maybe 1 minute. So I think plus they can do the program synthesis together. So I think roughly maybe let's say within 10 minutes we can complete the compilation.
Very cool. Okay, so what's your next step? Yeah, after parser.
So yeah, one thing is to joint optimization, the parser and the pipeline. And right now, actually, I'm also doing some eBPF code generation at this moment. So hopefully to see like some program synthesis can play a role in that part. So that's why I'm very it's very great you mentioned eBPF in this part as well.
Actually, Yao is doing some research about the verifier of the eBPF program.
I see. I see.
So,
I think verify. So I think my PhD advisors group have a lot of work in verifying the verifier of eBPF. So yeah. So
yeah. So we can discuss that offline. Yeah,
okay,
actually.
okay. That's awesome. That's awesome. Yeah.
Yeah. So, just out of curiosity, what is the most challenging part when you conduct this work? Yeah, how long does it take you?
So I think the main challenging part is to coming up with the optimization problems, optimization strategies. So the reason is you can see that the input packet string can be like more than hundreds bits big, like TCP header, UDP header, IP header, IPv4, IPv6. So it's not that hard to fit into a program synthesis problem, but the initial time take much longer. So let me give you a rough example. So if we only have two parser node, like we pass the TCP first and then pass the IP. That take around, if we don't have any optimization, that take around like more than 10 hours to get the result. We only have one parser node, or we only have two parser nodes. So that's why we think a lot about finding interesting domain-specific informations from the parser problems to reduce the synthesis time. So I think that's very challenging for me initially. Even make me thinking, hey, maybe we shouldn't do this project because of it's too long. Yeah. But fortunately, we found the interesting.
Yeah, but
like
finally it works.
Yeah. So but that take me a lot of time to think.
Okay, cool. So did you try ParserHawk on Bluefield SmartNIC? Did you try that?
Not yet, because previously I don't have access to Bluefield SmartNIC. So, and plus Bluefield have an ARM core there, right? So I haven't figured out a very great way to I haven't have a very concrete idea about how to treat the ARM core plus fixed function packet processing pipeline. Yeah, but technically, I think the Bluefield, they have a little bit different architectures. How to encode the ARM core, I may need to think a little bit more about that. Similar to Pensando, right? So that's
Yeah. Actually, I heard about that. I heard from Jia. He
yeah,
says that the Bluefield actually has P4 pipeline, but they didn't expose the interface to us. If
I
we
see.
if you can context the NVIDIA, they may give you the interface. Yeah.
I see.
Yeah.
Yeah.
So all the data functions can also be offloaded to the P4 pipeline. For example, if Bluefield exposes a Docker library, right? The Docker library is actually built based on a flow abstraction. So all the flow operations are conducted, offloaded on its own P4 pipeline, actually. But actually, if we use AMD Pensando SmartNIC, yeah, we actually have more accessible resources to of the P4 pipeline. Although actually one of my students, Jinghui is also here. Yeah, one of my students have tried the AMD Pensando SmartNIC. So although it is not a complete P4, yeah, but we can have a try. Yeah.
Sure.
Yeah. So next time maybe we if we have time, maybe we can just try ParserHawk on AMD Pensando and see what happens. Yeah, if there are new things that we can conduct research.
Yeah. We should see how the interesting from that particular architecture, and then
Actually, AMD Pensando has an onboard ARM cores. Yeah,
ah,
they have it has onboard ARM cores, hardware accelerators, ASIC, ASIC, and also programmable P4 pipeline.
I
Yeah,
see.
so now many researchers are consider are considering how can we use how can we have a better use of these heterogeneous onboard resources. Yeah.
Mm.
So it is
Mm.
actually a open question, an open question.
Yes.
Yeah.
Yes.
So yeah. So now time is almost up. Or just a last question. Yeah.
Sure.
So for a fresh student, yeah, what do you think is the best way to get started into this area?
Oh, I think so. If I were a fresh student right now, I would try to chat with more senior folks, either from academia and industry, to see what is the real painful problems, and then try to solve it. So I'm thinking that if we are, so there's a lot of tons of problems in the world, but some of them are not interesting, some of them are not urgent. So for the system research, I think we really need to see whether the problem we solve are whatever people need. And then when you collect maybe 10 or 5 problems, and you can combine it with your interest and your tactics to see how to solve that. So I think really finding the problem is the most important thing, because I think the community have some consensus about what we should solve. So that's something it's very important for fresh. And later you can find your problem, but in the beginning it's good to see what people are interested in, and then solve it from your perspective.
That's very useful suggestion. Yeah. So okay. Time is almost up. So it's nearly 12 o'clock, right? So we are coming to the end of today's meeting. So I want to give a big thank you to Yao for the wonderful presentation, and also to Xiangyu for joining us and sharing his experiences. So this paper actually brought up a lot of interesting points and sparked some great discussions. It definitely gave me a lot to think about. Yeah, so thank you all again for joining today's reading group. So all right, that's it for today. So good night and have a good day. See you next time.
Yeah, thank you, Cham. Thank you, Yao.
Thank you for joining us. Have a good day.
Thank
Bye.
you.